Can you hear me?
Yes.
Okay. I think my camera has gone bad, so you may not be able to see my face. In which case, I should just. Okay, let's begin. This is the last of the series of lectures that I will be doing on sequence-to-sequence models, which is the last component of recurrent neural of the series on recurrent neural networks. But this is not the last lecture on the topic. Next week we have two lectures. The first will be a lecture on transformers, but that lecture will be delivered by Howard Chen, who is one of my PhD students and who is an expert on the subject and who has a lot of really nice papers on it. And on Wednesday, we have a guest lecture on large language models by a professor from MIT. And so Professor Omar Khattab, and he used to be a TA for deep learning. So this is actually pretty special. And he again has made his name and fame on through his work on large language models. So it's a lecture that I highly recommend all of you attend. Anyway, let's begin with today's lecture. So here's where we are. We've been looking at sequence-to-sequence models where the model takes in a sequence and produces an output sequence, and there may be no apparent correspondence or synchrony between the input and the output. And here we saw that the kind of model we could use was this delayed sequence-to-sequence model, which would analyze the entire input. And then once the input was analyzed, it would use the result to generate the output. Now, the naive model shown on the screen we saw wouldn't work, but still, so here was the process. The input was processed by this first block, the encoder, and the result was processed by the second block, the decoder, to generate the output. And this was too naive because each word that is output depends only on the hidden state and not on previous output. So we saw that we really had to feed the word, the generated word, back in to the model. And so this was the simple translation model that we saw in the last class. So here's how this operated. If you gave it an input, like I ate an apple, then it would the first component of the model would process it and generate a hidden representation at the end of sequence marker. And then subsequently, the second network would use this hidden activation as the initial state and the start of sequence marker as the initial symbol and go ahead and produce a sequence of outputs till it encountered a terminal end of state marker. So this portion which processed the input was what we call the encoder, and the portion that generated the output was what we call the decoder. So the terminology derives from the fact that this first block derives some representation from the input which captures the essence of it. So in some sense, it encodes the input. The second block decodes this hidden representation into whatever output must be generated. So it's the decoder. And so here's where we were in the last class. Now, there are a couple of problems with this simple framework. And there's a problem on the encoder side, and there's a problem on the decoder side. Before I just spill the beans, uh, uh, I'd like to give you guys a chance to take a guess at what the problems might be. Anybody want to take a guess? Okay. All right. So here's this. Here's the problem with the decoder side. This hidden representation is being recurrently processed by the decoder. Now, this input could be some length. The output could be any length, right? It could be like 200 words of text. So in that case, by the time this recurrence has proceeded through 200 steps, the initial state over here is quite forgotten because the recurrence is getting a lot of stuff being fed in through here, right? And so the input that is uh, being given to the decoder will get progressively diluted. And so towards the end, whatever you generate might not have very much relevance to the input. Do you understand what I'm saying here? Right? And if you do, again, what is the main problem? The problem is that this thing is getting diluted through time. So if I were to ask you to fix this problem, how would you fix it? Any ideas? Any solutions? The problem is that this one here, aha. So Theodore has the right idea, right? Instead of having this be diluted recurrently, we know that every last one of these outputs needs to refer to this hidden representation. So here's what we will do. We can just pass it to every decoder step. Suddenly, this is no longer part of the recurrence on the decoder side, independent of whatever has been computed by the encoder. And so the decoder's recurrence has its own initial hidden state, which could be a level parameter. So this solves the problem of dilution on the decoder side. But then, as several of you had mentioned, there's also a problem on the encoder side. All the information about the input is being embedded into a single vector. So this single vector over here is supposed to capture everything that happened in the input, and it might work if the input is short, like I ate an apple. But then if this were a long sentence or a book with hundreds of words, then by the time you got here, stuff that happened early in the input is going to be quite forgotten. And so this one hidden state gets overloaded. And part of the reason for this is that there's recency bias. This is going to have much more information about the most recent inputs just before the end, and much less about those in the far distance. Now, when you're performing some decoding, the outputs over here can be related to any part of the input. And the fact is, every one of these hidden values actually carries information. So the recurrence in the input actually can end up losing this information because of the dilution through recurrence, right? And there's also the fact that the output words aren't just related to this one vector, because again, this vector, although it supposedly encapsulates everything that came in, is going to have some recency bias. There is a much more direct relationship between the individual output words and the individual input words. So Ishwar here is directly related to I. Aber is related to 8. And Gegessen is also related to it. You can see from these arrows that each word over here is more dependent or more related to some words in the input than the output, right? Than others, sorry. And so this is also lost by this model. How can we fix this? Now, how do I make sure that harbor actually refers to 8 more than it refers to apple. Now, one way to make sure that every one of these things is represented when it's being fed to the decoder is to just take all of these vectors and average them and pass this average to every decoder step. This ensures that every single output has some kind of an access to every single input. But, that's kind of inadequate because when you look at this, the same averaging applies to every input, which means that each one of these outputs sees the same average vector. And the process of averaging also dilutes information. So I ate an apple. Anne is going to just have 1/5 of the total weight of all of the inputs. And so whichever portion of the decoder is supposed to refer to Anne is going to have some trouble discerning it, right? And so we need something slightly different. What we will do is, again, just build on this basic idea. Okay, is everything I've said so far making sense? Okay, kind of. Somebody says kind of. Pierre, so where did I lose you? Can you tell me? Where did I lose you? Well, okay. I'm assuming that, okay, over here, which slide? This one? Pierre did, okay. Does it make sense that ish is more related to I than to apple? No? What is ish a translation of? Is it a translation of apple? Or is it a translation of I? This is German. Ish is the word I in German, right? So over here, this word ish is related to I and not to apple. Okay. Do you get it that each output word over here bears greater dependence or similarity to some of the input words than others? Right. So Apfel is clearly from apple and not from I or eight or am. Right? It's not the order. It's just that each of these words is related to a different we're saying. We never did assume there was an order correspondence, right? Well, you'll be training it. That's right. So, okay. And so assume that you have the trained model, and we're trying to understand how the model could operate before we begin considering other issues. And so averaging all of these. Now, one issue is that if you're only depending on this final hidden state, I is going to be quite forgotten by the time you get here. So when the decoder is trying to produce ish and searches for ish in here, it may not find it at all because ish is way back when, and the recurrence might have forgotten it. Does that make sense? Over here. So, okay, can I get a few more positive responses here so I know it made sense to everybody? Okay. And so one way to make sure that we don't lose things to recurrence is to just directly average these guys. This way, you at least make sure that when H is performing its decoding, it's seeing some of I, not quite as much as as it wants, but certainly when you average these guys and pass that to H is going to see a lot more of I than it does in this case. Does that sound right? Right, okay. But it's not going to see enough because in the process of it has to sort of discern the I from this average, and the average is munging things up. So what we would really like to do is something different. We would like to still compute a weighted average of all of these hidden states, except the weighting would be different for each one of these output words. So I'm sorry, there should not be a 1 over n over here. I keep forgetting to delete it. Ignore this 1 over n. The 1 over n is a carryover from here, okay? So how does this work? When you're generating ish, you would be computing some weighted sum of these hidden state values, and the weights are specific to this first output. And then you'd compute whatever you did and draw a word. And then when you compute the next word, you're still going to use a weighted sum of these hidden values as input, but now this would be a different weighted sum. So the weights are going to be different. And so you get a different, so this C0 is the context that has been derived from the input, from the encoder when it's producing ish. That's one weighted sum of these hidden state values on the encoder. That output is fed back to the network as ish here. And at the next time instant drawn from the encoder side is going to be a different weighted sum of these hidden state values. So these weights over here are going to be specific to the first output number 1 over here, assuming this is output number 0. And so then you draw habe and feed that back in. And now at the next time instant, the next output instant, so the difference is that these weights are different in each case I belong. Look at so I'm averaging these i's, but the specific values are going to be are different for each column, right? And so, yeah, we'll get to that, right? And so this is basically what we're going to do. At each time, how did this arrow get lost? Okay. At each time, we look at a different weighted sum of these hidden state values, and that is the context we'd be feeding in along with the input. And this would work if these weights could magically somehow be made to focus on the appropriate input word. For example, when you're generating upfill, somehow the weights must figure out that you must give maximum importance to H3 when you're computing the context vector. And that is the context vector that goes in when you're generating upfill. If you can figure out how to do that, then this would work. Does this make sense to you guys so far? Okay. So please, guys, be active on the thumbs ups if you don't, if you don't want to hold me up, because I am looking at that to make sure you're making no assumption about the length of the output, Shrey, because the output can keep continuing. The only thing you're assuming is that at each output, you're computing a different weighted sum of these hidden state values. Did that answer your question, Shrey?
So are the weights for each of the inputs, are they the same for each of the calculations?
So the weights, again, so for example, when you're generating upfill, you'd have some W0 times H0 plus W1 times H1 and so on, except those weights are very specific to this, to this time instant. So
So
at each
then
time,
for each batch, we would have different sequence length, then you are generating
the
something
input length is the same every time, right? So regardless
Mhm.
of, I could keep generating this forever. And at each time, you're looking at a very different weighted sum of these 5 values.
So if the number of weights are dependent on the output length, then isn't
The
it?
number of weights or the values of the weights is dependent on the output. So here, for example, when I'm generating gig SN, I'm going to have some weighted sum of these 5 guys, correct?
Mhm.
Those weights would be very different than when I'm generating Haber. It's still a
So
weighted sum of
are you
5 guys
saying like,
because
but how would it be different? Because there is the weight is of the hidden state, which is like, respective of the particular item, the input, and
So
then
okay, so now
yeah,
now you answer this question. How would we generate such weights?
that
Clearly,
that,
these
that
weights
that's
cannot be fixed, right?
right,
The
right.
weights must be dynamically computed for this to work, right?
Okay, makes sense. Yeah. Okay.
And the expectation is that if the model is well trained, this will automatically highlight the correct input. And so that's what we're going to figure out. So C is a single vector. It's an average of all of these h's, Leong. It's a weighted average of all of these h's. That makes sense? It doesn't have a length. This one over here, see, this is a context vector. And the context vector is an average of these hidden state values. So there's one vector going in, there's a vector going in at each time. And the specific vector that goes in is a weighted sum of these h's, and the weights differ by the output. So here's how the weight is computed. Ignore the 1/n, that's a bug, okay? So this is the key piece. The weights must be dynamically computed as functions of whatever's happening in the decoder, right? But then let's consider what happens when you're generating this output. So the input was I ate an apple, end of sequence. You started off with a start of sequence marker, you generated Hish, Haber, einen. And so einen has gone in here. And now you have to figure out somehow how to arrive at the weights with which to average these guys to compute this context vector. Now, clearly, the only things that you can use to compute these weights are stuff that you already have. And what is it you already have at this point? What do you have at this point? Can anybody tell me? When you're out here, what does the decoder have? It's going to have this S2, correct? The most recent thing. It has other stuff. It has S2. That's the most recent state. That's what is going to influence this guy most. And the word einen, correct? So we're going to ignore this word because it's randomly drawn. So the only deterministic information that the decoder has is the state S2. So clearly, whatever weight it's computing for each of these H's is going to be a function of the H itself and S2. We don't have access to anything else. Does that make sense? Yes or no? Right. So for example, if you want to compute the weight for H2, which comes from N, that weight is going to be a function of H2 itself and S2. The weight for H3, which is from Apple, is going to be a function of H3 and S2, and so on. So the weight at any output time t for any input I is going to be a function, some function A, of the hidden state at I and the output state at time t minus 1. Is this making sense? The equation at the bottom of the page. That making sense? Okay, so is C3 only added to the decoder's most recent states or all SI? C3 is specific to the third output over here, or the fourth, this guy, this column. Over here, you'd have C2. So we'll go through this in a little more detail, right? But then this is not enough. If I just randomly, if I computed a bunch of weights, and I have a bunch of H's, if I keep computing weighted sums of these H's, and if then there's no bound on what this context vector could be, right? Because as the input got longer, you're adding more and more and more things. And so the context vector that you'd compute is going to become a function of how long the input is. So how can you avoid that problem? How do you make sure that the context vector here is somehow bounded into the same range as these H's? Anybody? Sigmoid, right? Softmax. So here's what we're going to do. We're going to put this additional constraint. We're going to say that all of these weights are positive and they sum to 1, which is to say the weights form a distribution. So if the weights form a distribution, then basically you're computing a convex combination of these hidden state values. And so whatever context vector you compute is going to lie in the same general region of the space as the hidden state values itself. It's not going to exceed it on either side or it's not going to exceed the largest H value or become smaller than the smallest H value. Is this making sense? This requirement on W's. What about the rest of you guys? Can I actually see some thumbs ups, please? I'll wait for 25. Since there are 170 people in class, surely there are 25 people who can affirm that they got this. 23. Two more, please. 23. Okay. Why is it so hard? Okay. Anyways. So this one here doesn't guarantee that the weights will sum to 1 and form a distribution. And I have one weight for each of these guys. So how do I convert these weights to a distribution? Anyone? How would I convert them to a distribution? Anybody? Softmax, right? And so here's how it works. You first compute a raw weight for each of these guys, which is just a function of the hidden state and the previous state, hidden decoder state. And then you put, so I'm representing them as EI of t. EI of t is the raw weight computed for the ith encoder state at the tth decoder time. And so these EIFTs are going to be put through a softmax, and now you end up with a set of weights across all of these guys, which are going to sum to 1. And so here's your first poll. Let's see if I can pull this up. Can you see the poll? They don't. It tells you there are 3 questions. Okay, 5 seconds, guys. All right, let me terminate this. There are only 171 people in class. Here's what you guys thought. And let's see. The attention framework computes a different context vector at each output time step. True or false? First one. Okay. The context vector is chosen as the hidden encoder representation of the input word. That's assigned the highest attention weight. True or false? Is this true? You're computing the context vector as a weighted sum of the hidden states. So, the one with the highest attention weight will get the largest weight, obviously, but you're still always going to be computing a weighted sum of all of these guys, right? So this is false. And the last one, the attention weight is a function of the hidden encoder representation for the word in the most recent decoder state. True or false? True. Okay. So true, false, and true. Okay. And so finally, what is this raw function? How do we compute this raw attention weight? For that, no, because you're assuming that at least on the decoder side, it's keeping track of information. And so, yeah, it is an issue though. Okay. So let's look at how we would get this hidden state, this raw weight. There are different functions. The simplest thing is to say I'm going to compute an inner product between the state here and the hidden state here. That only works if H and S have the same size. If they have different sizes, then you have to stick a matrix in between the two, and you'd be computing a matrix inner product because this guy must be a scalar, right? And so this matrix can be learned. And there have been other uglier functions that have been proposed in the literature. So all of these basically are different functions that take in this S and this H and give you a scalar. You can come up with your own, but these inner products are the simplest and make a lot of sense. And then once we do that, these values can be put through a softmax. So let's look at a typical conversion process. And I'm going to be assuming this one here, where H and S have different sizes, and there's an intervening matrix, which makes it all compute to a scalar. So you'd have the input. Initially, the input is going to be processed by the encoder. You'd have a hidden state computed for each input word. And then On the decoder side, the decoder has an initial hidden state, which could be a learned parameter or a fixed vector, of all ones or all zeros. All of these have been tried, reported, or you could even take an average of these guys as the initial hidden state or some transform of it. They're different possibilities. All of them work just as well. And then this one, initially, at the very first output time, the only state that you have available on the decoder side is S minus 1. So you're going to compute the raw attention weights for each of these guys as the matrix inner product of S minus 1 and these hidden state values as given here. And then once you compute those, you put those through a softmax, and you're going to get one weight for each of these vectors. You take a weighted sum of all of these vectors. This annoying one of 1 over n must be ignored. You take a weighted sum of all of these vectors, and that gives you a context vector that is fed in to this recurrent state along with the start of sentence marker. And now the decoder is going to produce an output probability distribution for the first word in the output side, from which you draw a word and then feed it back to the network. Now, when you come to the next output time, you already have S0 available because S0 was computed in the previous time. So now S0 is going to be used along with these H's to compute a matrix inner product, which will give you a raw weight for each one of these terms. Those raw weights, the E's, are put through a softmax to obtain the actual weights for each of these H's. And then you can compute a weighted sum of these H's to get the next context vector. Observe, now the weights are going to be different than the previous time, right? Because we used a different argument as 0. And so this weighted sum, which is the new context vector, is going to be fed into the network along with ish to produce the next output, which is going to be a probability distribution again, from which you draw a word. And now that word goes back in, but now you have S1 available, which is going to be used to compute all of these weights. And with using these weights, you'd compute the next context vector, which is the weighted sum of these H's. And the next context vector is fed into the recurrent network along with Haber to produce the next output, and so on. And you'd keep continuing this process until you finally generated an end of sequence marker. So is this process making sense to you guys? Did this process make sense? Oh, okay. It's not even very hard to code. So I see 4 thumbs up. Thumbs ups? Can I have more, please? Like 1/6 of the class. The output is going to be a probability distribution over words. I'm sampling that to get the words, just as we did in the last class, right? Did I answer your question? Yeah, okay. So this is attention-based decoding, right? Here's at each output time, you process the input, then at each output time, you use the previous state and these hidden states to compute a raw attention weight, put them through a softmax, and use the resulting weights to compute a weighted sum of these hidden state values to obtain a context vector, which is fed back into the network. So this is the basic attention-based decoding, but then we can have some modifications to this. The most simple modification is something to call a key and is to split this hidden state into something called a key and something called a value. Now, what is the idea behind this? So let's say I am at this state, I'm at S4, then I must compute a weighted sum of all of these hidden states. And clearly, I'm speaking of the way the sentence is forming up. It looks like I have something that I can have one item of. So possibly a food item. So now when I get here, is it important to know that this is actually an apple that I have one of? Or is it enough to say that it's a food item? For the purpose of deciding which word to give most weight to, do you need to know the specifics of the word or just the general category? What would you think? For example, if I said I ate an, do I need to know that it's an apple to focus on it? Or is it sufficient for me to know that it's a category, that that's an edible something, right? So clearly, the weights don't need to know the details that this is an apple. It's enough for the weights to know the general category of the word. But the actual context vector, for that, is it enough for it to say that it's something edible, or should it know that it's an apple? Well, whatever goes in here. It should know that it's an apple, right? So you get two different levels of granularity required. When you're computing the weights, you don't need to know that it's an apple. To compute weights, it's sufficient for you to know that it's something that's a food item. But then when you're computing the actual context, you really need to know that it's an apple. So for the W, it's enough to have the category, but for the H, the specific item is required. Is that making sense? Yes or no? Can I have a little more enthusiastic? Guys in class, if you don't want me to just randomly call out names and ask you if you've understood, then please give me the thumbs up so I can see some 25 thumbs up each time I ask a question. All right? So at this point, I will be scrolling down this list of participants and seeing who doesn't have a thumbs up, and I will ask you, unless you actually, actively respond. Okay. And so we have two different levels of resolution required. And so here's what we will do. From the H, we're going to derive two vectors. One is called the key. The key gives you the coarse level of resolution, enough to say that it's a food item. The other is called the value. It gives you the finer resolution, which tells you this is an apple. And so when you compute the attention weight, you're going to use the key. Now, you have to transform this guy to have the same size as the key. So the transformed version is called the query. And the query is going to be compared to the key to determine the attention weights. And then once you have determined the attention weights, you're going to compute a weighted sum of the value. So the key tells you it's a food item. The value tells you it's specifically an apple. And to compute the weights, you're going to use the key, but then to compute the context, you're actually going to use the value. Did that make sense to all of you? So this is a big step up from what we just saw. And so here, the raw attention weight is going to be a function of the key and the query, and you get a weight. And the input to the decoder is going to be a weighted sum of the value. And that way you get both the coarse granularity for attention and the fine granularity for the actual context vector. And the special case is where, you don't bother to actually make these distinctions. The key and value are the same. The query is simply the state itself. This is just, us being not bothering to make the distinctions, but this actually simplifies explanation. So this is how I'm going to be presenting the rest of the slides, except when necessary, okay? So again, so far so good. So have you understood the model so far? The whole thing? Can I get 25 thumbs ups before I proceed? Okay, thank you, right? Once again, like in the previous lecture, what is the objective of this whole process? What do we really want to do? I gave it an English sentence. What is the characteristic of the German sentence that came out? What do you want it to be as an objective? Anybody? What would it have to be? Are you going to pick any odd German sentence, or it's going to be the most probable, right? This is simply a statistical model. We don't care about meaning. We don't care about anything. From a statistical perspective, you want to have the most probable German sentence given the English sentence, right? If the model is learned right, it will capture meaning and all the rest of it. But from a purely statistical perspective, from the machine's perspective, what you want to do is to pick the most probable sentence. And what is the probability of any particular word sequence? It's simply the product of the probabilities assigned to those words at each time. And once again, this is auto-regressive, meaning each output is fed back. So, the word that you choose here is going to affect everything downstream. And so this is the same problem as the one we saw in the last class. We must pick the word sequence for which the probability of the product of the probabilities of the individual words in the sequence is maximized given the input. Is this making sense here? And how would we go about this? Anybody? So you can see the complexity, right? Anytime I draw a word over here, that's going to change everything downstream. So all the problems that we mentioned in the last class still hold. And we need to bypass that, right? So if instead of ish over here, I'd chosen a different word, then I'm going to get an entirely different sequence. And so, we saw how these choices can affect our ability to get the most likely sequence. And so we suggested a solution in the last class. What was that? Anybody remember? What was the solution? The beam search, right? So at the first time, you're going to get a probability for every word. You pick all of the words, but then you keep only the top k, in this case 2. And so you only expand the network out. You make 2 copies of the network on the decoder, and you're going to keep the 2 most probable words. Then at the next, but then when I'm performing this computation, I need a context. And each of these is going to come, because I'm in different branches of the tree, they're going to have different, they're going to have different previous states. And so the context vectors will be different. Then once again, over here, each of these is going to produce a probability for all the words. So I can expand the network out fully and then just keep the 2 most likely, right? This is what I will have. And again, the context vectors for the 2 are different because this guy is going to use the hidden state from here. This guy is going to use the hidden state from here. And so the weighted sums will be different and you'd have different context vectors going in. And then once again, you're going to have different, each of these is going to produce probabilities for every word in the vocabulary. So you can expand the whole thing out and keep just the top 2 and so on. And keep continuing. At each time, when you pick the top 2, you're not just picking the top 2 based on the local probability, but based on the product of probabilities down the entire path, which is what is being shown over here, because these are the 2 most probable partial hypotheses for which you have to factor in all the words on the path. And you can keep continuing this until the current most likely path ends in an end of sequence marker. Or you could continue to say, I'm going to produce that n most probable outputs, which is fine too. So is all of this making sense? The beam search. Okay. So it's a hyperparameter. You can have 4, you can have 10. The more paths you have, the better your decoder is going to be, the more probable it is going to be. Now, how do we check if this works? For that, we have to look at these attention weights. Do they really work, right? And so here's some results from the first paper where they used it for machine translation. Here they were trying to translate English into French. So here's the English sentence. The agreement on the European Economic Area was signed in August 1992 period. So when it's translating the first word, the word the word le is most related to the. So you'd expect the attention weights to be most focused on the. And that's indeed what it is, right? The word accord in French relates to agreement. And so you'd expect to see the most attention weight to agreement. And so you can see, there's almost a one-to-one correspondence between the English and German and French words. And so the entire attention thing has a roughly diagonal pattern. Except when it comes to here, this is very interesting. In English, we say the European Economic Area. The word European comes first. In French, the order is changed. Zone économique européen, right? And so zone, l'accord sur la zone, my pronunciation is awful, is zone relates to area. And so you see that the attention weight, the maximum attention weight is actually to area. Economic pays attention to economic. And when it's trying to produce European, it actually it pays most attention to European. And so you have this attention pattern which follows the correspondence between the input and the output, and where the order correspondence is flipped, the attention pattern actually flips. So this is very pretty, don't you think so? Or did you even understand what this figure means? Okay, right. So the meaning is distributed across the three acronym words. Does that contribute to confusion? If you have one meaning distributed across multiple words, you're going to see spreads of attention, like this guy's paying attention to 2 words, right? And so on. So generally, the whole thing really works. It's very nice. And they have some examples in the original paper for machine translation. And this attention-based method was the one that actually made Google Translate really functional suddenly in October 2016, because we went from being able to not being able to translate things very nicely to being better than humans pretty much overnight. So we've seen how a trained network can be used to compute outputs. You convert one sequence to another, right? But then how about training? Again, when we train the network, you're going to be given the training input. The training data are going to have the source sequence and the target sequence. So it could be I ate an apple, ich habe einen Apfel gegessen. During the forward pass, you're going to pass the input sequence through the encoder. And on the decoder side, at each time, you have an output that's a probability distribution over words. So we have an issue over here. What is the issue? How does this differ from the standard forward pass for inference? We saw this even in the previous class. What was the issue? Anyone? How did this order? Both input and output are being fed in, right? We saw in the last class that in your standard model, the input goes in, the output comes out, and this is compared to the target. But that's not what's happening over here. The input and the output are going in, whereas you wouldn't have the output at inference time. And that's because we need them out here, right? So this differs from your standard training. And of course, in this, again, now you can compute the divergences at each time, where the divergence is the cross entropy between the probability distribution output by the network and the next word. And these divergences can then be backpropagated. And in the process of backpropagation, you would also be updating any parameters of the attention function. Because if you have performing a matrix in a product, there's a matrix in the middle, that's a learnable parameter. You'd also be updating those parameters. Now, here's the key piece. When I give it both the input and the output, this in fact performs what is called maximum likelihood estimation of the model. The forward pass of training takes in both inputs and the ground truth labels for generation. So the forward pass, as we just saw, is not like regular inference because both of these are going in. Whereas in regular inference, only this would go in. This would not go in. So why, again, are we not using regular inference for the forward pass? Why are we also passing the output in? Anybody remember from the last class? Why don't we just do this, right? The input goes in. Why can I not draw? Yeah. Why can't I just have input and output and compare it to the target? Anybody? So exactly, right? When you start training, why would this not work? The target is a Shaba and an Apfel gegessen. But in the beginning, the network could be producing something like this, because the network is really bad at the beginning. How do you compare these two guys? You cannot really, right? How do you compute a loss between these two sequences? Quite impossible. Which is why we sort of pass in these guys also to make sure that there's a one-to-one correspondence between the actual output and the target output. Is this making sense? Why we do this? Right? Okay, and this is what they call teacher forcing, because the output is the label itself is also being passed into the network. So, of course, now this is completely cheating because you're passing the label back in. So you have something of a midway solution where every now and then you draw the word and feed it in. So some of the words are the words from the ground truth, some are not, some of them are actually drawn. And then you compute your divergence. So if you do this carefully enough, you will still have a one-to-one correspondence between the actual and desired outputs, and you can still compute your divergence and train the network. So, but then the process of drawing a word from a distribution and feeding it in is a non-differentiable differentiable procedure. And so in order to backpropagate derivatives through this business of drawing, we use something called a Gumbel trick, which is on the slides, but I'm not going to go over it right now. So that's the basic model. And there's some other things we can do, like bidirectional processing of the input sequence, where you have the encoder has bidirectional inputs, or you can have different forms of attention, local versus global attention. There have been a whole ton of papers on this, on these various extensions. And one common extension is the so-called multi-head attention. So where in what we just saw, we just computed a key and value and used that to compute the attention, the context. But then you could compute two different sets of keys and values here and two different queries over here. And if you train it properly, maybe the first key and value look at parts of speech when they decide to figure out what to pay attention to. And the second set of keys and values look at something else, like the semantics. And so you manage to capture different aspects of the data when you compute your context vector. So this is a simple extension of the standard attention model. Is this making sense to you guys? The multi-head attention? Yes, no? Shrey, if a single head is going to only capture one aspect, right? So for example, if I consider this one, if I think of the input in terms of, the semantics, maybe I want to focus on I. But if I want to look at it in terms of parts of speech, maybe I want to focus on this guy, right? So depending on the view that you take of your data, there are different portions of the input that are important. Does that make sense? Right. And so when you just have a single attention head, you're picking one of these. Why pick one? Why not have multiple? So we're going to have multiple keys and values. And so for instance, the attention that you get based on the first key and value, key and query, might be focused on part of speech. And the one that you get on the second one might look at part of semantics. So you get two different context vectors and you feed both in. That's the multi-head attention. That makes sense to all of you guys? Can I see some thumbs ups? Unless like 25 of them. Okay. So that leads us to our second set of owl eyes. Okay, 10 seconds, guys. 5. Okay, let me end this poll. So here's what you guys thought. Let's ask you, which of the following will give you the optimal decode? Full tree search or beam search? The full tree, right? The beam is a heuristic. Over here, in a query key value based attention mechanism, the key and value are used to compute attention rates. True or false? It's false, right? You're using the key and the query. Remember? And so key and value come on the encoder side. The query comes on the decoder side. The key is the crude information, the value is the fine detailed information. Multi-head attention computes a separate set of keys and values for each head at each input. True or false? It's true, right? And so the multi-head attention computes a separate query for each head at each output. True or false? Also true, right? You must have one query corresponding to each key value pair. Training with teacher forcing computes the theoretically correct loss and minimizes this. True or false? It's false, right? Because the theoretically correct loss must be based on free decode. We're cheating. It makes sense? Then this last one is false. This is okay. Let me continue, right? And these models change the world. Attention-based models are basically at the heart of all AI, but with a minor twist, and we'll get to it in a minute, right? So here, and you can apply for everything from machine translation to captioning images. This is a beautiful example where they use it to caption images. The encoder is basically a CNN, which goes over the image. The decoder is paying attention to different parts of the image input when it's generating its output. So this one is captioned as a woman is throwing a frisbee in a park. When you look at what it's paying attention to when it produces frisbee, it's actually looking at the frisbee. A dog is standing on a hardwood floor. Now the caption is wrong, but even so, when you look at what it's paying attention to when it says dog, it's actually looking at the dog, right? And this one is really nice. A giraffe standing in a forest with trees in the background. When you look at what it's paying attention to when it says trees, it's everything except the giraffe. It's beautiful, right? So these things really work. And so to recap, we've looked at various forms of sequence-to-sequence models, which are generalization of recurrent networks. And there are lots and lots of papers on this, and it's going to appear in homework 4. Except that we're going to be looking at a small variant, transformers. So the recap is the simple sequence-to-sequence model had this structure. The input sequence fed into a recurrent structure, and the hidden activation at the end of sequence marker was the final representation of the input, which is fed into the decoder, right? And this overloaded this guy from both sides. So the attention-based mechanism obtained a context directly from the input and fed it directly as input on the decoder side without recurrence. Moreover, the context vector was computed as a weighted sum of the hidden state values on the input side, where the weights were specific to the output time. And so it solved a couple of problems. But in this, if I'm actually explicitly paying attention to different ages when I'm generating this context, then does this recurrence have any meaning anymore? Remember, the point of the recurrence was for this hidden state to somehow aggregate information over time. And that made sense when you were passing it to the decoder. But if the decoder is explicitly looking at each of these guys, does this recurrence make sense anymore? What do you think? Yes or no? I see one no. What do the rest of you think? Does it make sense? So it shouldn't, right? it could complement each other, but okay, Daniel, why does it make sense? Why do you need to aggregate information into H4? You might have a point, right? And just superficially, at least, to maintain order, maybe. And let's deal with that, right? Superficially, at least, this makes no sense, right? At least from the perspective that the decoder is explicitly factoring in each of these, means that you don't have to load all of these guys into H4. Yes, there are some other issues, but H4 doesn't need to capture I8 and Apple. H4 can just represent EOS in context. Does that make sense? Over here. Without recurrence, H4 is not referring to H0 through H3, is it, Miguel? H4 is not even looking at these guys, correct? And so each of them is just representing the local information, and it's not trying to aggregate the entire sequence preceding it. So without recurrence, H4 is only looking at EOS. With recurrence, H4 would be aggregating I8 and Apple. Right? Yes or no? What do you guys think? So, and this makes more sense, correct? Because the decoder is explicitly looking at each of these guys. So, okay, let's get rid of recurrence. Recurrence is a pain. But then this still has an issue, right? So that problem is this eliminates context specificity in the encoder embeddings. For example, what is this? Forget about Anne. I'm learning a representation for Apple. When I say Apple over here, am I referring to the company, the computer, or the fruit? In order to make that out, I have to look at everything in the neighborhood, right? So although it makes sense for everything to be local like so, it doesn't make sense for it to be completely local because you'll be missing information. Is that making sense? Over here, right? So I still don't want to use recurrence because it makes no sense for this Apple to be overloading I8 and I just want to represent Apple. But then the specific representation for Apple must take the context into consideration. So how would I do this? So David, if I use a TDNN, I went to the store and bought I went to the Apple store and bought bought a Macintosh, right? So now the Macintosh is clearly a computer, but I had to look way back when, right? So TDNN, it had to keep expanding the windows. And at the same time, when I'm looking at a window, I'm looking at a whole lot of other garbage, which I'm not really interested in. When I'm generating the representation for Apple, I just have to look for cues as to whether it's a computer, a company, or a fruit, and the rest of it is irrelevant, right? So how could I do that? How could I get an appropriate context-specific representation for Apple? Anybody? How would I do this? Have we seen something that already works? Here's what we're going to do, right? I'm going to use the attention framework itself to introduce context specificity. So here's what I would do. For every word in the input sequence, I'd have a initial representation, say using an MLP or an embedding. Then from each one of these, I'm going to compute a query, a key, and a value. And then let's say I want to update the representation for I. I'm going to look at I'm going to pick up the query for I and apply it against the keys for every other word in the input. And so that was going to give me, and then, I put those raw attention weights through a softmax. I'm going to get a bunch of weights. These weights are the weights with which I must be combining all of these edges to get an updated representation for I. It's paying attention to both itself and to everything else. And so then I'd use these weights to get a weighted sum of the values for all of these guys to get the updated representation for I. Is this making sense, this process? Yeah. Right. Can I see some thumbs ups, guys? Some 25 of those, because I'm just going to take off from here. 16, 17, 18, I'm counting. I need 6 more. Okay, thank you. And
Prof,
then I can do the
explain this
same.
slide again.
Okay, thank you, right? Did you get this? That from each of these H's, I can get a query key and value
Yes.
just by having 3 different matrices, correct? Then I can take the query for H0 and apply it to K0, K1, K2, K3, K4. And that will give me a bunch of attention weights for H0, H1, H2, H3, and H4, right? Yes, do you get that? Okay. And then I can use those. What was the query? The query is computed from H0 using this WQ, right? Sunmyan? From H, I have 3 matrices which will give me the query key and value. Did that answer your question, Sunmyan? Yes, okay. And so then I can use these weights against these values and get an updated representation for I. Then I can use so the updated representation for I is going to be the weighted sum of all of these values. And so this is the self-attention block. You're just paying, the input string is paying attention to itself. I can do the same thing. Now I can use the query for 8 and compare it to all the keys for H0 through H4 to get their weights, and then get a weighted sum of their values. And that's going to give me the updated representation for 8. Then I can use the query for AN and use that to get an updated representation for AN, and so on. And so I can get an updated representation for every one of the words in the sequence. That makes sense? Yeah? Okay, so can I get why? So what do you mean by normal attention, Brian? Here. This is all you've got. So you're paying attention to everything you have. That's it. That is normal attention in this setting, right? Okay, again, can everybody confirm that this was understood? I'd like to see some 25 thumbs ups before I jump ahead.
Prof, so the self reference, the self in this case is just because it's paying attention to itself in addition to others.
There's nothing else that it's paying attention to, just itself. Right.
That's kind of confusing because I thought it was
Right.
paying attention to itself and others.
Wait, so I'm looking at only the encoder. There's nothing happening at the decoder, just this left-hand side. So the input is paying attention to the input. That's what is meant by the self-attention.
Okay, got it.
Right. So yes, David, if the word input was super long and 8 was paragraphs away, in this simple setting, it would still influence self-attention in the same way. Okay, we'll address that in a minute. Okay, and so we can now, but David, that's a good question, and we'll see how we can do this, how we can address it. And so this is what I'm going to call my self-attention block. Now I can have, this is a single head self-attention block, but then I can generate multiple sets of keys, queries, keys, and values. Each of them is going to generate a different updated value of I, and I can concatenate all of them to get an updated representation for all the words. And so now this is a multi-head self-attention block. Is this making sense? The multi-head self-attention. Okay, and so that's your multi-head self-attention. And then we typically mix the whole thing up, and then you get your updated representation, which is your multi-head self-attention block. But then this is going back to David's problem, right? And the encoder can include many such blocks, no need for recurrence. Now, the encoder in a sequence-to-sequence model can replace recurrence through a series of multi-head self-attention blocks. But this ignores relative position. This is to answer David's question. When I get an updated representation for Apple, is the importance of "and" the same, whether it's the word immediately preceding it or whether it's the word 20 words away? Would it be the same in every case? Or should I be paying more attention to "and" when it's the immediate preceding word than when it's far away? What do you think? What would you do? It has to be immediate, right? Because the word "and" occurring out here has no relevance to Apple. But if the word "and" occurs right here, then I certainly know that this is not the name of a guy, right? Yes or no? Can the rest of you give me some thumbs ups on that? Okay, I'll wait for 25 and proceed. Okay. 22. Can I get 5 more, please? Oh my good God. 23. It's dying at 23. Okay. So how can I fix this? Here's what I'm going to do, right? This is something crazy. So I have my sequence of vectors. Why is it vanishing? Holy moly. How do I keep it from vanishing? Okay, so I have my sequence of vectors, right? And if this is apple, this is my, apple. If the word "and" occurs here versus the "and" occurring here, I want them to be entirely different. I want it to pay more attention to "and" here and less to "and" over here. So how can I make this happen? Here's what I'm going to do. To each of these guys, I'm going to add some noise. And the noise has a very specific characteristic. What is the self-attention? Attention is basically correlation, right? You're looking at the correlation between the query and the key. That's what an inner product is. That making sense? That an inner product is a correlation? Yes or no? Yeah. So here's what I will do. I'm going to add some noise. And the noise is going to be such that it's a time series. And the noise is going to be such that the correlation between the noise at any time and the noise is further away falls off with time. So because I'm adding this, that means that the correlation between this A and an "and" that occurs immediately before it is going to be greater than the correlation between this A and an "and" that occurs far away from it. Is this making sense? Over here. Okay, but then this must have a specific property. I want to pre-compute this noise sequence. And then if I pick up any one of these guys, the correlations must fall off like this. If I pick up this guy and look at the correlations with its neighbors, it must fall off like this, right? So that's the kind of noise we're going to generate. And the distance, the correlation must depend on the distance. So how do we do this, right? Note that what we are looking with are actually word embeddings, right? And so what we will do is generate something called a positional encoding. And the positional encoding is got some properties. It's noise. So because it's noise, no two positional encodings are identical, meaning looking at the positional encoding. If you had a table of positional encoding versus time, just by looking at the positional encoding, you would know the absolute time. But that's not the important piece. Also, you don't want the noise that you've added at one time to be, bigger or smaller than the noise you've added at any other time. So these positional encoding vectors will all have the same norm. Does this make sense? This one here. This term here, okay? And then finally, the positional encoding will have this property that the positional encoding of t plus tau is going to be some m of tau times p of t. What this means is that now the correlation between pt and p of t plus tau is going to be the same regardless of t, and it's only dependent on tau. At any t, the correlation between pt plus tau and p of t is simply going to be a function of m tau. Is this making sense? So we got this property, right? So how do we create m tau? What is it's some matrix. So how do we create such a sequence? This is where the original paper had this position vectors computed from sines and cosines. The position vector always had the same norm at each time. No two position vectors were identical. And you could show that p of t plus tau equals m tau times pt, where m tau was a rotation matrix whose values depended on time. And so as you went further and further away in time, the two position vectors got further and further apart in angle, and their correlations died. This makes sense? What we have here? The general idea? And so let me go on faster. You just add these positional encodings to these guys initially, and then just have the rest of the multi-head attention block. And so this is the self-attending encoder. No recurrence, you manage to capture context, you manage to capture recency, and everything is in one place. And now these representations can be used with your recurrent decoder. But then, if we can do the encoder with recurrence, can we, without recurrence, can we not do the same thing with the decoder? Turns out yes, right? Again, on the decoder side, in the encoder, we computed query key and value. And when you're computing the update for 8, you had all the words, including I and Apple. So if I were looking at the updated representation for it and the encoder side, to update this guy, I'd compute a weighted sum of all of this and get the update, both stuff from the past and the future. But on the decoder, because you're generating words one at a time, ich esse einen Apfel, right? When you're generating einen, Apfel has not yet been generated, so you cannot be paying attention to the future. There's nothing in the future. And so this is something called masked attention, where at each time you only pay attention to itself and everything in the past, and everything in the future is masked out. That's that one change on the decoder side. But besides that, you still have everything just like the encoder masked self-attention, and an MLP, you can even have you typically have multi-head masked self-attention followed by MLP to mix things up, which gives you a masked multi-head self-attention block. And the decoder itself has many such blocks to generate the output. So did this make sense? How we eliminated recurrence on both sides? Masking prevents the cheating, yes. No, it doesn't prevent the cheating. I mean, if in inference, during inference, you just don't have access to the future. There's no notion of cheating, right? During inference, you don't have these guys. You could pre-allocate them and mask them out. It's more like an engineering thing, right? So we just ignore. Okay. So, and this is your entire model. Let me give you this final poll. Actually, this is the third poll. Can you guys see the poll? Okay, 10 seconds, guys. Let me end this poll and ask you the questions. Here's what you guys thought. And let's see. You cannot have bidirectionality in the decoder because you don't have access to the future Kaiser. So here, self-attention computed for an n-length input sequence requires the computation of an n cross n attention weight matrix for each head, true or false. right? Because everything is paying attention to everything else, so N cross N. Masked self-attention is only required in the first layer of the decoder. Subsequent layers see the entire output of the previous layers and can use full self-attention, true or false. This one. It's going to be false. Doesn't matter which layer you're in, you don't have access to the future, right? You cannot combine recurrent layers with self-attention attention layers, true or false. You can combine anything with anything, right? Positional encodings are different in the encoder and decoder because self-attention in the decoder is masked, true or false. False, I mean, doesn't really matter, right? So only the first one is true. And so this was this famed attention is all you need paper, where they eliminated recurrence. And of course, one last thing they did was to make these things residual networks. And this thing changed the world. So I have a bunch more slides on this. There's an encoder-decoder model. GPT is just the decoder side. It's a language model. BERT is the encoder side. It derives representations from the data. And as we know, self-attention replaces recurrence. It can be used to in regular sequence analysis settings as substitute for recurrence. And currently, it's the state of the art in pretty much all of AI. I'm not going to continue on this because we have a complete lecture on transformer models on Monday. So stop right here. I have some more slides. You guys can look them up if you want to. Actually, you must because they may just appear in the quiz. And I'll take any questions. Any questions?